Welcome back, Gen Chem 2. I love it. We're going to continue in our series of our integrated rate law. So before you start this video, you may want to have either your computer with some Excel or a graphing calculator handy, because we're going to go through a set of data and actually manipulate that data and plot that data in a linear plot. So you may want to just hit pause for a second and make sure you have something that you can graph with. This is going to be fun. Okay, awesome. So we are on our series, and this is part of our integrated rate law. And in our integrated rate law, we are going to look at first order in this video. So we're right smack in the middle of a series of videos, which I love it. Okay, so I want to go through the full process on this video for how to handle an integrated rate law problem. And the first thing I'm going to do is I gave us a sample problem from a textbook. We're going to look at a specific decomposition of thionyl-chloride, and we're going to monitor it as a function of time. Okay, so just stop right there. That's giving us a hint. All right, look at our data set. We have time and concentration. Okay, I love it. So concentration and time, that is giving us a clue as to what kind of problem this is. That could either be a general rate law or general rate expression, or our integrated rate law. And then we're asked to determine the order of the reaction, the rate constant, and a concentration at 2000 seconds. Okay, so this is an extremely helpful, extremely common question in kinetics. This is awesome. This gets at the heart of so much in kinetics. And so how do we figure out what we're even doing? How are we going to get the order of the reaction, the rate constant, and a concentration? Well, right away, we never really got an order from a general rate expression. So we know that it's not that type of problem. And if we have concentration versus time, and we're solving for order, rate constant, and a concentration, that's what tells us this is the integrated rate law. There's only one way to do that. So the trick with the integrated rate law we saw in our first video is that it actually depends on order, because you have a different series of equations depending on the order. So if it's zero order, you have one set, first order is another set, and finally second order is another set. So the first thing you always have to do in these problems is determine the order. And how do we determine the order of a reaction? Well, there's really three general ways. The first one is with the rate law. We saw that in the beginning of kinetics when we compared two experiments. The only way to use that rate law is if you have data for concentration and rate. And in this case, we don't. We have concentration and time. We do not have rate data. So then our second is to actually take time versus concentration and use our plot method. And what we're going to look for is a linear plot. That's what we're going to do in this video. And then third is, what if you have a crafty instructor that words in there the units for K? Our units can also tell us the order. So we're going to focus on number two. How do you use the plotting method in order to figure out the order of your reaction and then figure out your rate constant and your concentration at a specific time? Now, another indicator for this problem is you're thinking, wait, Dr. Morty, just shut the front door. Why can't I go look at my data and just read for 2000 seconds? What? Because your data table on purpose stops at 1500 seconds. So you've got to actually calculate a concentration that is not part of your data table. The only way to do that is to plot it. So I'm going to ask you to pause your video here and enter this set of data on either Excel or your calculator. And then we're going to manipulate it. So go ahead and hit pause and enter that data. Okay, once you've got your data entered, we're going to monkey with it. So in this plotting method to figure out the order of our reaction, we're going to compare time with our concentration. Okay, and if this is linear, awesome, that is zero order. That's what we saw in our last video. But if it isn't, then we're going to compare time to the natural log of concentration. And if that is linear, that is first order. And then if that's not linear, we keep going and we compare time to the reciprocal of concentration. And then if that is your linear plot, that is second order. So I go ahead and plot all three. Okay, why? Why do you need to plot all three? Because you can't always tell. You really need to look at your linear plot. So let's start with the first one and let's look at that plot. Let's plot time versus concentration and we'll see what that looks like. And then if you're on Excel, what I do in order to get the natural log of that thionyl chloride is that I'll highlight this cell and then I'll go under those math functions. I'll find natural log, and then I'll highlight this cell. And then go ahead and highlight this little bottom corner and drag it down. And now you've just done the natural log of that whole data set. And then we can do the same thing for this reciprocal. What I do for reciprocal, because it's easier, I highlight this cell, I type in equals 1 divided by, and then I highlight my concentration cell. And then do the same thing. On this cell, I kind of put my cursor over this corner and I drag down, and now we've got that whole data set made. Okay, now let's plot. Let's plot the first one, time versus regular concentration. And let's see what that looks like. Okay, so now when you're looking at this, you're thinking, all right, you need your plot with your line equation and your R squared value. Now this is where Excel is 100 times easier than your calculator because we really need this R squared value. We have trust issues in our class. I'm not going to tell you the order of your reaction. I'm just going to give you a data set. And if you were doing this as a homework problem or a test question, you'd take a look at that R squared value and remember what we said in the last video, closest to 1 wins. Okay, so I'd take a look at that if I were doing a homework problem and say, dude, that's super close to 1. This is a 0 order. Unless you plot all three. So this was our first set of data. This is just our concentration. We did not manipulate it. But then look what happens if we plot our natural log. Oh, there's our trust issues coming out. Look at that. Look at that R squared value. This one is the winner. And this was the natural log of the concentration. Gave us that linear plot. So this means that this is the winner. And because we took the natural log, this is an indicator that this is first order. And for good measure, let's compare that last column of data. Let's compare that we just plotted the 1 over concentration. And look at what our R squared value is. Okay, now we're getting away from 1 again. So you definitely want to pause here and you want to plot all three of those sets of data. Each one of them is the same time column, but then here's your concentration. Here's your natural log of concentration. And then here's your reciprocal of concentration. So hit pause on here, take a minute, and get those plots rolling. Now, if this is the first integrated rate law video you watched, you got to stop. You're in the wrong order. You should have watched the 0 order where we talked about plotting. And then in Wednesday's class, we'll actually plot some of these together to make sure we feel good about putting these on Excel and getting to that linear plot. Okay, so this whole process, once we figure out that this is our linear, this gives us 2 answers to our question. This gives us the order. It's first order. And then what else do we get from our line equation? Shut the front door. This is your K. So right away, your rate constant and your order come right from that Excel plot. That's beautiful. So what's left then is to solve for that concentration at 2,000 seconds. And why we had to do this first is we needed to know which set of reactions to use. For a first order, we have a specific set of reactions. So let's scroll down and let's write out the equations for first order. Okay, so for first order, we've learned them a couple different ways. So I'm going to write a few options. We wrote them in our first video as the natural log. Okay, at some time over our natural log of our initial. Okay, that's one way to write them. And then we also wrote it as the line equation. Okay, so what do we know here and what do we do with this? So this is our series of equations for first order. And then once we've figured out that whole part, that's the hard part. Now we just plug and chug. Okay, what comes from where? Well, this is our goal. We're going to solve for this one. Our A, we commented way back in the day that we'll default to 1 on that. Our K came from our slope. Let's just double check that. That is on our, there it is. Okay, that is your K. And then our time that we're solving for, we are solving for 2,000 seconds. That was in the problem. And then the natural log of our initial concentration, we've actually already figured out. That is on our data sheet. We let Excel calculate that for us. That is right here. So minus 2.303. So let's go ahead and write everything in there. Okay, so we're going to solve for the natural log of our SOCL2 at 2,000 seconds. I'm sorry, I keep hitting that. Okay, there's our K. And what would our K be if this is first order? 1 over seconds times that 2,000 seconds that was in the problem plus that natural log of our initial. Okay, so now we're about to solve for the natural log of that concentration. So when I do the math on that side, I'm getting a negative 2.883. And then how do we actually get to the concentration then? You know, your natural logs, that's E. And I am getting 0.56 molar, okay, when I solve for that. Awesome. So wait, we learned in our 0 integrated rate law video that, hang on a second, you need to double check that number. Does that fit your data? It should be less than your last data point. because you're running off the table, right? At 1500 seconds, you had 0.0647. So does this make sense? Yeah, it's less than that. So that totally makes sense. So that sounds like that is our big money answer. All right, so we just did a whole problem. Let's turn right around and do this again for second order. So I'll see you in the next video.